All right. First, we look at these two concepts, dense index and sparse index. So we look at from different point of view. From the name, you can guess the meaning a little bit. The dense index. So what's that? Yeah. All right. So its definition is very simple. Yeah. For this type of index files, yeah. So when you create it, for each record in the original data file, you need to create one index entry for it, 1-to-1 correspondence. Then it's dense, right? Yeah. So that means you do not skip any record in the original files. Yeah. That meaning. Yeah. All right. That's different from what we learned before. Yeah. The last time the primary index, yeah, we will do the comparison next soon. All right. Yeah. Yeah. Here, if we recall the primary index, it's not dense. Yeah. So here, let me just, some of you may already forget the meaning of this primary index. So here, let me describe the main idea a little bit. We call the primary index. Yeah. All right. So first, for the original file, yeah. So let's suppose we have, oh, all right, I need to change the color. All right. Suppose this is our original file or table. Yeah. All right. We have several columns. All right. Yeah. Here, let us assume we use this column to create an index file. So we can sort it, right? Yeah. Yeah. Because the way we create index file, if it's possible, we will sort it. Okay. Yeah. Sort the file, sort the whole table based on this column. Right. Yeah. All right. But after we sort it, then when we create an index file, here we use the primary index. Now we try to save. We try to make our index file as small as possible, but we can still do the fast search. That's the basic idea. Because the goal, we want to do this key-based search very fast. Yeah. So with this goal, we try to save as much space as possible. In that way, we do not have to store for each record there. We do not have to store one entry here. Yeah. So we can jump. Okay. We can jump in this way. Yeah. All right. Yeah. We can skip a few entries. Yeah. All right. A few record, skip it. Without losing anything. Cameron Battle, Luke Frederick, new student, 2 students came in after I do the roll call. All right. Yeah, so the reason, yeah, so some of you may forget the details. The reason in the hard disk, yeah, so let me, because we need to go back to this, data storage on a hard disk. All right, hard disk. We have sectors, right? Yeah, because we have cylinder, we have, a disk, two surfaces for each slice of a disk. We have two surfaces, all right? Yeah, two-sided storage. Then we divide into sectors, okay? Tracks, sectors like that, tracks like in this way, okay? All right. Yeah, and then the unit is a block storage unit. We call the block. Okay. Storage unit we call a block. And why block? Because when we load the data from hard disk to main memory, we do not want to load small amount of data, because every time a trip to the hard drive is pretty expensive, okay, relatively slow. So we want to load reasonable amount of time. So that's why we use this block concept, one block of data. So how large is the block? You may like to know how large it. Yeah, because the old time, when we start, the block is 0.5 KB. Yeah, so that's the, long time ago. But when the technology improved better and better, the current block size typically in 4 KB. Okay, yeah, so you can imagine every time one trip to the hard disk, this much data is loaded. With 4 KB, you can store many records, right? Yeah, think about it. Depends on how large is your record. So you can put, at least usually dozens of records in this block, okay? Yeah, so here, for each block, so here, the idea for this primary index, so one entry for one block. Each block, you only need to store one entry, that's enough. Because that entry can tell the loading program which block is the right one to be loaded. That's the idea. That's enough. So one entry for one block, okay? Or that one entry is the representative in that block, okay? Yeah. So the block, yeah, so there is a block. The first record in the block, the first in the block, we call it anchor record. Anchor one, okay, yeah, very first one. Yeah, because that first one will tell the location. The first one has address, right? Its address tells the starting location of that whole block. Yeah, so that's the, most convenient one. Yeah. So you go there, you load the whole block. All right, so here I give you the background. Yeah, so this is the primary index. Then you can see it's not dense, it's sparse, right? It's sparse, yeah, because in that block, all these records skip it, okay? All these, the remaining of the block, all these records skip it in primary index. Okay, yeah, but you can still do the binary search on these entries. Yeah, later I will talk about, how to do the binary search. Okay, we can look at it more details there. Yeah. So that's the primary index. Okay, yeah. All right, yeah. Later, when we do comparisons, we will come back to this topic again. All right. One index for one block anchor. Yeah. Okay, yeah. So that's what we learned before. Yeah. 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 I feel many of you may already forget this part. So let's pick up. Yeah. What we left before. Another one, sparse index. Yeah. So this primary index, sparse index. Yeah. All right. Yeah. So the sparse index has index entries for only some of the search values representative. And the reason very simple, because those, if we only store part of it, some of the entries information, we can do the binary search. That's good enough, right? Yeah. So that's the reason we do not have to store entries for all the records. Yeah. That's the idea. We can make our index file smaller and we can do search faster. Yeah, think about the binary search. If we only have smaller number of entries to be searched in a binary search, we can do faster, right? Yeah. When you do comparisons, you can use smaller number of comparisons faster. Yeah. And it's good enough because you need to load the whole block. Right? Whole block. You cannot split in the block. You cannot load a partial block because it's not efficient. One trip is very expensive. You just load small number of data inside that block. That's not efficient. Right? Yeah. All right. Comparison. Yeah. Compare these two types. Yeah. But why there is some reason to use dense index. The reason is very simple, because you may not be able to use the sparse index, right? If you can use actually, the first try, you need to consider primary index. If you cannot, then you consider other types of index file. Yeah. If you can sort the data, the first index type you want to use primary index. That's the reason this primary index is most popular index type, most popular type. Okay, yeah. Because most of the time, 90-something%, most of the time, we can sort data, right? Yeah. Our data fields can be sorted. With a total order, we can sort it. Then we can apply primary key. If it can be sorted, we can apply primary key, index, primary index. But we need to also consider very small chance the data cannot be sorted. Then this dense index can be used, even if the data cannot be sorted. Yeah. A dense index is larger than a sparse, but it is still useful, yeah, because a dense index supports unordered file. If it cannot be sorted, you can use dense index. Yeah, because in that way, one entry for one record, you do not miss anyone. And you cannot apply binary search. If it cannot be ordered, how can you apply binary search? You cannot, right? Yeah, you cannot. Yeah. But your index file, you keep track of all the records based on some unordered field. Yeah. It will be slower, yeah, in this way, because you cannot use the binary search. It will be slower, but you can create an index for it. Yeah, you can still do it. Yeah. All right. Yeah. So that's the difference. Yeah. All right. Next, let's look at the details. Retrieve a block with a given primary key. If we have the primary key, yeah, but here we need to avoid confusion on this primary key. What's the meaning of primary key here, right? In this context. Yes, I hope, yeah, because the thing is, this terminology, yeah, because we know there is another popular meaning of the primary key, right? In the table, we have primary key, but here it's different. Yeah, it's better to use a different name. But here, it still use this primary key name. Yeah. So that caused a lot of confusion. Yeah, so we will see. Yeah, I will try to, give you try to tell the difference, this primary key and our older primary key. All right, two different meanings here. All right, yeah. Given a search key K of a record, here we assume we use the primary index because 90-something% of the time we use the primary index. So our main focus is on this primary index. Remaining part, the percentage is very small. Yeah. All right. Assume, primary index is constructed based on the field. We can sort the table data based on this key field. This field, yeah. All right, primary key. Okay, we can sort it. All right. This field, yeah. It may not be a key field, all right? Yeah. A key in the field. Yeah, here, this key. Yeah. We mean some number, yeah. Some data, it may not be number, string, data value. Yeah, this key, just the data value. All right. Yeah. Then we do the binary search on the primary keys. Yeah, here. The primary key here, not our old meaning primary key. Its meaning is the keys in a primary index. That's its meaning. Yeah. I hope, those people, they create a different name for it. Yeah. Otherwise, yeah, quite some people, they will get confused, right? Yeah. This primary key. So this primary key in this context, it means the keys in a primary index. That means, yeah, so it's called primary key, right? Not our old primary key. Yeah, because our old primary key, think about this. Our old primary key, in each table, most of the time we have primary key, but sometimes we don't have primary keys. All right, yeah. All right. But even we do not have primary key in a table, we may have other fields that we can do the sorting, right? We have other fields, we can do the sorting. Then we pick any field, we can do the sorting on it. We can create a primary index, and we use that field, and we use the, keys in the primary key index entries as the primary key. Think about that. Another meaning, primary key, not our old meaning primary key. Yeah, very confusing, very confusing. Yeah, but that's the way, people use in this way. Yeah, yeah. I hope, the community should create a different name for this concept. Yeah, otherwise very confusing. Yeah. All right. Yeah. So let's continue. So we do the binary search. But when we do the binary search, what do we get? Yeah. So look at K of I. That's the entry. Yeah. So that I, little I, the entry location in the primary index, K of I. Okay. Yeah. And the location I, the primary key value at that location. All right. Another primary key, K of I plus 1, two adjacent primary keys. Okay. Yeah. And the given key, you can, when you apply the binary search, you will find two adjacent primary keys, and the given key is in between. Yeah, in between these two primary keys. All right, left hand side less or equal, right hand side strictly less than. Yeah. Because in that way, you will know which block to load, right? The block this one points to, right? Yeah, yeah. There is a pointer. For this entry, there is a pointer. That pointer gives you the block location that contains this record. This record must be in that block. Okay, so you just load that block into the main memory. Yeah. So let's continue the next step. All right. Require that the original data ordered on the indexing field. Yeah. That's the, our basic idea, creating an index file. First, we need to sort it. If it's possible, we sort it. If it's not possible, then we find another way. Yeah. All right. Yeah, but here, to be able to use the primary key, we know it can be sorted. So we create a primary index. All right. Yeah. So original data ordered on the indexing field. All right. Then get a pointer P of I. Yeah. Pointer will tell you the address location of that block anchor. Block anchor. Anchor the record address, the first record in that block. Yeah. This block containing the record with the key K. And we don't know where it is, right? We just know that record is inside that block, but we don't know where it is. And we don't want to find that record inside that block because it takes too much time. And we don't want to do the search inside that block. All right? We just load the whole block into the main memory. Yeah. All right. Yeah, this block containing the record somewhere. Yeah. Yeah. load this block into the memory, the whole block. Here you can imagine, let's say 4K, that 4KB. Yeah, that amount of data is loaded one trip into the main memory. All right. After you load this block into the main memory, then you do the search because you need to find that particular record. Yeah. Then you do the search. Inside the main memory, you find the right record in the disk block. All right. Yeah. Load that whole block. Okay. All right. The last step, find the record in memory. Main memory. We know do the search in main memory much faster, right? Yeah. Much faster than doing the search inside what? Inside this hard disk, right? Yeah. Hard disk. Yeah. We know hard disk, the data access time much slower than memory access time. Yeah, that difference quite big. Okay, yeah. Yeah. You can even imagine 100 to 1, that kind of ratio. Okay, close to that. 100 to 1, 100 times slower. Then you don't want to do the search. If 100 times slower, you don't want to do the search inside the hard disk, right? Oh, yeah. But regarding find the record, you need to do another round search, right? How do you find search? But what kind of search? You need to think about, right? Yeah, typically we have two types. One, linear search, right? Or sequential search. Second type, binary search. These two types. Now, inside the main memory, we need to find the right record that, yeah, because with the given key, this is the key is used to tell us which record is the right one. But when we do that search, do you think we should do linear search or binary search? Okay. Think about it. The answer is linear search, not binary search, because the data is not ordered in the block. All right, data not ordered in the block. Okay, data is only ordered in the primary index, but yeah, primary index based on the key, it is ordered. But in the disk block, original data is stored. Original data stored, right? But we do not sort original data, right? Now, original data, we want to keep the original order. We do not want to change its order. Okay, think about that. Original data, we do not want to change its order. We keep the original order. Yeah, so you cannot assume the original data is ordered. Okay, you cannot. All right. Then after you load the whole block into the main memory, it's not ordered. The records inside that disk block is not ordered. Then you can only do the linear search. You compare one by one in the natural order in the block. The first record, second record, third one, slower than the binary search. But a good thing first, the disk block is not large, right? Yeah, here we just use 4KB. The disk block size, it's not large, first thing. Second, when we do comparison, it's inside main memory, it's much faster, right? Yeah, it's much faster. Yeah. So even slow linear search in relatively small number of records, we can do pretty fast. Then, in this way, we can get our overall search time pretty fast. Yeah. So this procedure tells you the necessary detail. How do we find a record in a table, in a database? Yeah, here, in this way. Okay, yeah. All right. All right, yeah. I think we only need to know this much detail. Yeah, yeah. That should be good enough as our background. Okay, all right. Then, yeah, the last topic of this part I want to explain a major problem with a primary index. Yeah. Still, yeah, based on our understanding at this point, it looks like pretty good. Yeah, primary index. Yeah, we know, 90-something% of the time we use this primary index, we can apply binary search, pretty fast, things like, but there is actually some pretty big problem when you use this type of data storage. Yeah. Some problem occurs when data is added and deleted. Dynamic data, think about our data in our applications in the business world. Our data keeps coming in and go, right? Come and go frequently, all right? Dynamic. When the data comes in, you need to add a new data item into the current storage structure. Some problem could happen. Then delete the data, or some data item is gone. After deleted, then you need to remove it from your storage structure. Then you may need to modify your storage structure after the deletion. So a lot of things could happen. Yeah. A typical problem for ordered file. Yeah. When you have ordered files, you have this problem, because you need to maintain the order. You need to pay a lot of cost maintaining the order information, store the data. Yeah. After insertion and deletion, to recover the ordered structure, the cost is high, pretty high. Yeah. Because you need to modify the whole storage structure. Think about if that some special storage structure is pretty big, how much time you need to recover that structure. Okay, yeah. Change in the primary key. Let's look at how much change work we need to do in that situation. Yeah. Move records to make space for a new record. Think about after insertion, do you need to provide a new location for the new entry? Think about that, right? New location. Okay. Yeah. In your index file, your index file has a special structure, and you need to find a new location for the new entry corresponding to the new record. All right. Yeah. Change anchor records in some blocks. Yeah. Think about after deletion, some anchor records you may need to change. Yeah. After deletion, yeah. Even after insertion, right? Yeah. Because insertion, the new entry contains that anchor information. Yeah. Change some index entries. Yeah. Some index entries, you may need to do some change. Yeah. All right. Yeah. Right. So you can see, even if we use the primary index, actually, we need to do some important efficiency related work. Yeah, here. The things here we want to do them efficiently. We know we have some way to do it. But the question is, can you do it efficiently? All right, efficiently. Yeah. Here, what do you mean efficiently? Here, I need to provide you some real sense. How do we do it efficiently? Yeah, all right. Okay, here. Because it will relate it to how to store the primary index file. Okay, here. We consider two ways to store our primary index file. Well, how do we build a structure for our primary index file? Yeah, two. Yeah. One is we use a linear structure. Yeah. Linear structure, what's a linear structure? Array. Array is a linear structure, right? Yeah, sequential order, you know. You have indices, you know, arranged in order, linear structure. That's array, all right? But there is another one. Binary tree structure. Binary tree structure. It's not a line, it's a binary tree. Okay? More complicated than the linear structure, right? Yeah. But now efficiency issue. If you use linear structure, the search efficiency will be big O of n. Big O of n. Yeah, I hope you know this meaning. Okay, yeah, because we assume you have learned the algorithm class. Yeah, big O of n. Yeah, linear search. But if you can store your primary key in a binary tree structure, the search efficiency will be big O of log n. Look at that. That's huge difference. From big O of n to big O of log n. That means when we store our primary index, we should take the binary. Yeah, actually, yeah, I like to say not, yeah, not binary tree. Tree structure, how about that? Yeah, because binary tree, each node, you only have 2 child nodes, right? 2 limited. So we will use the tree structure. Yeah, because each node, we can have many child nodes, multiple child nodes, more than 2, much more than 2, yeah, actually. Okay, yeah, so not binary, just tree structure. Okay, yeah, all right. Then log base, yeah, then it won't be log base 2, yeah, because log base n. Yeah. Each node, we have n different branches to go. Okay, yeah. In that way, we can make our search operation much faster. Okay, even if we have large amount of data, we can make our search operation very fast because we have this tree structure. Okay, all right. A more advanced data structure is needed. That's the tree type data structure. More advanced, yeah. For this class, yeah, because we don't have much time left. So I cannot talk about the details of those trees, special tree structure. Okay, all right, yeah. Yeah, but here, yeah. I can give you, yeah. So one type of data structure is called B tree. Yeah. So we do not call this B not binary, yeah, because multiple child nodes, not two, multiple. Yeah, but we call the B tree, all right? Yeah. So this is the first one. Second one, an improved structure. Yeah, similar, yeah, we call the B plus tree. Slightly better than that B tree, yeah, but basically the same, yeah, slightly better. Yeah. It's pretty complicated. These two type of tree structures, pretty complicated, okay, yeah. But the most important features of these two data structure, because they can handle the dynamic storage of your primary index efficiently. Yeah, think about when you have insertion, you can insert into this B tree or B plus tree. Yeah, here, let me just use B plus tree. Yeah, because it's a improved one. Okay, B plus tree. So when we need to insert a new entry into our primary index, we can make our insertion very fast. Yeah. First, we can find a location using the big O of n log n, very fast. All right. Then, after we find the location, when we do insertion, yeah, so that B plus tree in that node, we leave some space for the insertion. Yeah. So the design is very smart. It's pretty complicated, but it's very smart. Yeah. So by default, it leaves quite some space for the insertion. So you can just do insertion immediately. Okay. Yeah. But sooner or later, when you do insertion in one particular node, that location, sooner or later, that node capacity will be full. If it is full, you need to split the node. Split one node into two nodes. Okay? That split operation, you need to do a lot of work. Okay? That split, relatively more expensive. But you do not always do split. Okay? Yeah. After certain number of insertion, then you do split. Okay? Yeah. So you try to reduce the occurrence of the split. Yeah. Then you can grow that tree. Yeah. Split. Yeah. The tree keeps growing, more and more nodes. Okay. After deletion, you merge. Yeah. Yeah. Because deletion, first you just do the deletion directly inside that node. But sooner or later, the number of entries stored in that node becomes smaller and smaller. Sooner or later, you need to merge two nodes. That operation relatively expensive, but you do not always do that. Only after certain number of deletion, then you merge two nodes. Okay, yeah. Then you can shrink. Yeah, if you have a lot of deletions, you can shrink your B plus tree. Yeah, the operation pretty complicated. So here we do not need to know the details. here I just give you some description. Yeah. Before, many years ago, I talk about the details. Yeah, but most students cannot understand that part. Too complicated. Yeah. So now I just describe it a little bit, yeah, to give you some idea. The detail, yeah, so we skip it. Okay, how to do split, how to do the merge. Yeah. So we skip that part. All right, yeah, so we finish this topic, yeah, this indexing topic. All right, next we go to the complex queries. Yeah, but here I want to introduce this exists function. Very useful, very simple. Yeah, from its name, you can see we just want to check if certain things exist or not. Exists function. Yeah. But in our query, if we use this function, we can handle many complex queries. So let's look at the detail. The meaning is so simple. Yeah. Check whether the result of a correlated nested query. So we have inner query. Yeah. In the inner query, so here, this exist function mainly apply to the inner query. We want to check our inner query result is empty or not. That's simple. Yeah. Yeah. So simple, easy to understand. Yeah. But very powerful. Yeah. All right. True, this function returns true if the nested query result or inner query result contains at least one tuple. Yeah. Not empty, at least one tuple that exists. Okay. Yeah. Function true. False if the nested query result contains no tuples. Yeah. False. Yeah. So true, false, then you can determine you selected or not. This function mainly used to check some condition. Yeah. So you use this function to implement some condition. Yeah. It is used to implement some condition. Yeah. Implement some condition, we have other ways, right? Yeah. Yeah. We have many other different ways. This is just one of the ways you can use. You have many different ways. So this method provides you one useful and powerful way to implement some condition. Okay, yeah, all right. Similarly, not exist function. Yeah, sometimes we want to do the opposite, right? We want to do the opposite, not exist. Yeah. Yeah. More convenient. So this version, there are two versions. Exists version, not exist version. Yeah. So we just pick a convenient one to represent some condition. Okay, yeah. True, it's empty. Yeah, not exist. True, empty. Yeah. Opposite. Yeah. False, not empty. Yeah, yeah. All right. So one of the two versions you can use. All right. Exists and not exist are typically used in conjunction with a correlated nested query. Yeah. For the inner query part, you want to, really check certain condition. All right. Yeah. So let's look at some example. Yeah. All right. Using exists function. This example. Yeah. Let's compare. Yeah. All right. So we use two different ways. One, our old way, without using this function. Then a new way using this function. Yeah, we can compare. Yeah. Here, you may not see a simplified version. Yeah, it may not be simplified, but yeah, sometimes this way you can get your logic straight better. Yeah, your logic thinking, your understanding a little better, but you need to build up some experience using this way. Okay, yeah. Look at this one. Select first name, last name from employee as E and the dependent. The condition after table join condition. Yeah, the main condition. All right. The first employee's first name equals the dependent first name, and employee's sex equals the dependent sex. Yeah, okay, yeah, a child. So we want to find a child with the same name as the employee and the same sex. Okay, yeah, that question, yeah. And this one you saw already, it's pretty simple, right? Not very difficult. All right, so now let's write the same query, but using the exists function. Just a different way here. Yeah, not a simpler way. Yeah. Just a different way. Okay, all right. This time we put our inner query. So this is our inner query. Okay, yeah, our inner query. Yeah. In the inner query, we fix employee, right? Yeah. So outer query employee is fixed. All right. Then we take that fixed employee and we do this inner query. We compare for each dependent of this employee. Yeah. Yeah. Because first we need to make sure the dependent belongs to this employee. All right. Then the name should be the same, sex should be the same. As a whole, that query result exists, not empty. All right? Yeah. Think about that. Think about that. Now, can we not, yeah, we only have 5 minutes left. Yeah. Let's just compare the difference in these two. You can see there is a little different. They're not completely different, right? They're not exactly the same, slightly different. What I mean, the different, that is the, you know, the, yeah. All right, yeah. Yeah, actually, yeah, slightly different, yeah. These two versions for the query results slightly different. Yeah. Why? Think about, yeah. But actually, yeah, here, for this particular example, that difference may not happen in the real world, but here, if we talk about the general query result, that could happen. Yeah. So what do I mean here? Yeah. Because here in the real world, this happened, even if this case happened, that means the first name of the dependent, the same as the employee and the same sex. If this could happen, it usually happens only once, right? It cannot happen more than once, right? For one employee, how can you have two child with the same first name? You won't, right? Yeah. But by the logic, okay? So here we do not do this, you know, dependent thing. Think about, we may do the query for some, you know, other different things in business, okay? Then you may have the condition, you know, for that employee or for that product. So whatever for that, you may have more than one match, right? So for one employee or for one product, okay? Yeah, you satisfy certain condition. But when those conditions satisfy, you may have more than one. Think about it. In the first version, you will repeat that product information, more than one, right? Yeah. Because when you have one match, you list it. When you have second match, you also list it. Okay, all right. But look at the second one. Exists. It exists. That means the inner query result not empty. That could be 1, that could be 2, that could be 3, could be multiple tuples, right? Yeah, one tuple, multiple. Even it happens multiple times. Yeah, but you go through the other query, that product, that employee only comes out once, right? Yeah, because you go through the employee table from beginning to end. Each employee, you only go once. You only take it once. All right. Yeah. Then you get into the inner query, to do everything inside. Yeah. So when you find a match, you display it, and then you go to the next employee or next product. Okay. So you do not repeat that employee more than once. Yeah. The first version you may repeat more than once. Okay. Yeah. Think about that logic. Yeah. So not for this particular one. Yeah, this one dependent, you won't have more than one. So you don't worry about that. Okay. Yeah. But so here, when you use the exist function, you can see if you want to avoid the duplicate display, this way, exist function way is better, right? Yeah, think about it. This way is better. You do not need to apply distinct keyword. Yeah. The first way, if you want to remove the duplicate records, you need to put the distinct keyword, right? Distinct keyword, we know if you put it, your query will be slower. Yeah. Remove the duplicate tuples. Some special algorithms need to be applied that will slow down your query. But this version, no distinct, you do not display duplicate rows. Yeah. No distinct keyword, you do not apply that special algorithm, it will be faster. Think about that, right? Yeah. So, yeah, try to get an understanding in this example. Okay, exists. It has its advantage. Yeah. All right. So let me stop here. I have another big example. Yeah. So today I ran out of time, but the next example is the hardest example of this whole class. The very hardest one of this whole class. Now I leave to the next time. Very difficult to understand. Not long, but difficult to understand. Yeah. So we will talk about that next time. Okay. All right. So that's it. Yeah.